Hello everyone, I welcome you to the second session on abstract model authoring. In the first session, we have seen what is CAENexus, what is CAE geometry, and we have understood what is abstract and its significance in CAENexus context of knowledge capture and automation. And we have also quickly seen the CAENexus workflow. So in today's session, let's visit each abstract entities in more details and to understand how CAENexus gets to the information from abstract to actual geometry model. There are some definitions and rules that needs to be understood thoroughly, which will help to author the abstract models effectively. So let's see those rules in details. So abstract model authoring deep dive. So here abstract entities like class, closure and relation, and how the attributes are transferred from abstract entities to real geometry, that we will see in today's session. So first one is volume class, a three-dimensional abstract entity. A three-dimensional volume class represents an abstract fluid space. For example, in this model, a class size B is attached on three legs of a viaduct CAD model. In the abstract model, we have attached mesh size attribute on size B class. Let us remind ourselves that we have attached mesh size attribute on abstract class and not on geometry. The class itself is assigned to three components, that is geometry part on which we want to specify the expected mesh size. Thus, let us understand what we specify a class which represents a physics, in this case the mesh size, on geometry component in CAD, and then we add an attribute or a behavior of that class in abstract model. Now we will see in simulation model how this mesh size attribute is attached on abstract class is transferred to real geometry. So let us first check the class tab, which is equivalent to abstract model, and we can cross check if we have assigned the class to expected geometric entities. So here we have selected size B and it is highlighting these three legs. It is also highlighting the mesh size attribute. So we can see that mesh size is expected to pass on these three legs. Now let's check the component tab. We should observe that the CAENexus has created three components and three corresponding attributes. The model tab, which represents the geometry, the model tab is the one which actually gets meshed, exported to the solver files. Here we can see that the software has transferred the mesh size attribute on three regions which we are expecting. The next abstract class entity is boundary or closure. It is a two-dimensional abstract entity which bounds the three-dimensional volume class minus interface of volume class. So it is a closure. So please note that we will see interface of volume class shortly. For example, in this model, the fluid class is attached on all parts of viaduct model. So in abstract model, we have attached a wall attribute on boundary of fluid inside. I hope it's very easy to imagine where all the wall boundary condition will transfer. Now let's see in simulation model how the wall attribute is transferred to geometry. The best practice, we should first check class tab and check if our class highlights the correct geometry regions and boundary faces. So now we have clicked on boundary of fluid inside, and it is highlighting the attribute, and it is highlighting all the walls of the geometry on which fluid class is attached. So let us, for time being, let's ignore this inlet and outlet surfaces. Once we go through the relations, we will understand this inlet and outlets boundary condition specification. Now check the component tab and model tab. So this attribute is split into 4 attributes in component tab, and it is split into 4 attributes in model tab. So this is how in CAENexus the attribute is transferred from abstract model to real geometry. So next abstract entity is interface. It is a two-dimensional abstract entity which a three-dimensional volume class will share with other three-dimensional volume class. This is a kind of relation between two classes. Note here that our boundary definition of class earlier has excluded the interface surfaces. We strongly recommend to avoid using interfaces to specify attributes. This is because interface is defined with any other volume class and which may not be evaluated uniquely across the geometries given its definition. But for consistency purpose, let's go quickly through the interface with size attribute attached on interface of size A. So mesh size attribute is attached on interface of size A. So as a best practice, let's quickly check in class tab. So here when we select the interface of size A, it is highlighting the attribute and it is highlighting the interfaces of the connector pipe, that is interfaces of size A, as size A is attached on this connector pipe. Similarly, check the component tab and model tab. So in connector pipe, when we select the interface, it is highlighting the surfaces, and in volume 1, that is connector pipe, it is showing 3 surfaces on which this mesh size attribute is transferred. Next abstract entity is surface class. It is a two-dimensional abstract entity. For example, in this model, the size A attribute is attached on outlet legs of viaduct model, and in abstract model we have created mesh size attribute on class size A 2D. It's quite easy to understand that the specified mesh size attribute should be transferred to surfaces that we tagged in the CAD model. Now let's see in simulation model how this mesh size attribute is transferred from this 2D abstract entity to real geometry or real faces. So first check the class tab. So class tab, it is equivalent to abstract model, and we can cross check if we have assigned the class to expected geometric entities. So here we have clicked on size A2D and it is highlighting the attribute, and it is also highlighting the surfaces on which we have attached the class. So now check the component tab and model tab. In component tab we can see that outlet pipe 1 surface and outlet pipe 2 surface. On these two surfaces the size A class is attached and it is highlighted in the geometry. We should observe that CAENexus has created two separate attributes for these two surfaces. So relations need little more imagination. So class relation is an abstract entity which represents common or shared entities between classes whose dimension and or side will be evaluated based on classes involved. So following class relations can be defined in abstract model, that is 3D 2D, 3D 3D, different classes and 3D between same classes. Relations are much more dynamic in nature and are very useful to make compact abstract models. So first one is 3D 2D relation. So here, for example, we have attached outlet 2D class on these two surfaces and we have attached fluid class on these two legs. So try to imagine the relation of R fluid and outlet 2D. So on this relation we have attached the outlet boundary condition, and if we check the simulation model, so first check class tab as it is equivalent to abstract model. So in class tab, if we select this relation, it is highlighting these two surfaces, and here in attributes we can see that the outlet boundary condition is defined on relation between fluid and outlet 2D, that is relation between 3D and 2D. So we can similarly check component tab and model tab. So in component tab, the two attributes are created as they are the different two legs components, and in model tab this attribute is split into two as there are two surfaces on which or face uses on which the attribute outlet boundary condition is passing. So next is relation between 3D 3D, the different classes. Let's create a relation between size A and size B. So try to imagine which surfaces will get through this relation between size A and size B. So on this relation of size A and size B, we have attached mesh size attribute. So in simulation model, we can check in class tab, when we select this relation, it is highlighting these three interfaces as size A is attached on connecting pipe and size B is attached on these legs. So similarly in model tab and component tab, we can check how this attribute is transferred. So in model tab, there are three surfaces on which this mesh size attribute will get transferred. So next relation is 3D relation between same classes. So we have attached fluid class on all these four components and we have created a relation between fluid class. So try to imagine through this relation which surfaces will get evaluated in simulation model. So on this fluid class relation, we have attached a non-physical, that is the interior boundary condition, and in simulation model we can check how it is transferred. So we have created this R fluid relation, and on this relation we have defined this non-physical attribute. So once we select this R fluid, it is highlighting these interfaces surfaces in class tab, and this attribute is split into three in component tab, and also in model tab there are three surfaces on which this attribute is transferring. So here is a quick chart of how attributes are transferred from abstract entity to geometric entities. So attributes attached on volume class will transfer to the respective regions or volumes. The attribute attached on 2D class will transfer to respected surfaces. Similarly, boundary or interface of volume class, that is again 2D, it will transfer to respected surfaces. Then boundary inside or outside of volume class, it is a 2D abstract entity, it is transferred to face uses. The relation between volume classes, same classes and different classes, it is a 2D abstract entity, and in model tab it is equivalent to surfaces or it will highlight the surfaces and relation between volume class and surface class. It will evaluate as a face use or 2D side. So thank you for watching this session. See you in the next session.